talk about class hierarchies. We're not. We're going to talk about templates. So we're going to fall a little bit behind. Every semester, there will be times when we fall a little bit behind, times when we get a little bit ahead. You know, we'll get to the material that we've outlined in the syllabus, but turn the mic down a little bit. One other thing here, there's a notice that says 2 former students now working at Facebook will be interviewing during their career. This is from last year, so I forgot to take it off. So the good news is 2 students from Facebook came to interview our students. The bad news is it was last year, not this year. Okay, so. Come on, what are you doing? Okay, let's connect. All righty. So, I'm still getting students coming to me with using code, my code that's out of date. They say, why doesn't this work the way your demo worked? Because you're using code that's out of date. The only thing I can promise, I have code all over the place. I've got XML document in 7, 8, 9, 10 different places on the college server because I don't do a very good job of cleaning up. So I guarantee that you will find the latest stuff in these Project 1 Help Spring 18, or Project 2 Help Spring 18, or Project 3 Help when we get to it. Guarantee the code there will be up to date. Also, I am putting most of the demonstration code in handouts repository CPP. I used to have a repository with each course. I'm going to get rid of that. I'm trying to consolidate places where the code is so there's not so much, less possibility for getting more than one version of code on the college server at any one time. But please, please, I've said this before, I'll say it again, go to these Project Help. This is where, if you need to use some of my code, this is where you'll find the current versions. Don't go to some other place on the college server and pull it up. Okay. I don't remember whether I talked about this in the class. I think I might have started it but not finished it. This is in SU repository CPP, so let's go there. Actually, I looked at that. Let me just go to pull it up from here. Yeah. So stop me if we've covered this. Stop me. What's in this demo? So in an earlier demo, we did a simple callable objects demo, and I demonstrated a lambda and a functor and a function pointer. Just a very simple demonstration. This, what I'm doing is I'm expanding the variations that we're going to look at. The syntax is going to get a little more complicated. So I want to do the simple thing first and then look at this demonstration. So I have function pointer callable objects, functor callable objects, lambda callable objects, and I'm going to invoke them all. I'm going to show this invoke function, this invoke a set of overloaded functions that will accept any of those callable objects. So let's look at invoke. So I have an invoke function that accepts a callable object T that takes no arguments and returns nothing. I have a invoke function that accepts a callable object and a parameter and invokes that callable object with that parameter and returns nothing. I have a invoke function that accepts a callable object. Accepts a callable object and a parameter, and now it has a return type R, and it's returning that type. I have one more type that we'll use with member pointers that passes a callable object. This is going to be a pointer to a member function, an instance of the function, a parameter, and so now I have this callable object of that takes the instance and the argument and returns the value. We're going to see variations of all those things. Did I talk about this last time? Wei Heng? No. Okay. Okay. Couldn't remember whether I did or not. So the easiest things are functors and lambdas. Let's look at functor. So functor is any class that implements operator paren. So this happens to be a functor that accepts a parameter and returns a string. And I'll invoke it with the invoker that's overloaded to handle that case. So what this particular functor does, just a simple little demo, doesn't do anything useful. It accepts a parameter as a argument to its constructor. It accepts this parameter and stores it away. And then the operator paren accepts the same class of parameters, P, and all the functor does is say this passed parameter is the same as my stored parameter or it's not. That's all it does. A little demo. Nothing useful, but illustrates the idea. Okay? And here's how the functor is used by itself and with a functor. So here I have functor. So this is the constructor. This is a constructor call. This is a functor of int, the parameter type where I had the template parameter was parameter. Now it's an int. I've made that. I've specified that to be an int, and I am passing an integer for this functor. So I'm creating this functor f, and it's storing this 42 away down in its its member data. Now I'm going to call the functor's operator paren by saying f of 42. These are not the same thing. This is a construction of a functor passing it that integer argument, and I can tell it's a constructor because here's the type. Okay? And this is an execution of operator paren. This is absolutely equivalent to f dot operator paren of 42. Okay? And all it's going to do is compare whether this is the same as that. In this first case, it will be. Now I'm going to use the invoke function, and I'm going to say invoke of standard string f of 53. Here I'm passing it 53. It's stored 42, so it'll come back and say they're different. Okay. So now one thing about these, the return type of this operator paren is string. The template type inference works fine with the arguments, but it doesn't do type resolution on the return type. And the reason for that is I don't have to ever use the return type. An application can, even though this functor operator paren returns a string, the application code doesn't have to use it. It could just say f of, without ever specifying whether whatever, without ever saying string equals, it just says f of. And so how would the compiler know which one to use? It wouldn't. So it does not do type resolution on the return type. So here, the way we get that to work, we have to help it. We say, invoke standard string. Here I'm telling it the return type is going to be standard string. Okay? It's doing type resolution on this. This is a type T, callable object. It's doing type resolution on this. I passed it an integer. But it can't do the type resolution on the return type. So here, so here's this functor of standard string G, hello, 687 world, and and now I execute the functor, and now I'm invoking the functor using that invoke function. So now, when I run it, so here I constructed it with 42. I just executed the functor with 42, and it says the parameter and value are the same. Now I'm executing it with 53, and they're not going to be the same. Instance holds parameter 42, parameter and value are different. And it does the same thing for strings. Okay? All right. So functor case is fairly simple. I want to talk now about lambdas. Here's a lambda. And here's lambda.cpp. And now, before I talk about that, let's take a little excursion and go up here and look at CodeSnap. Tell you what, before I do that, let's do, let me go back and let's look at this for a minute. So what's going on here? This lambda, I'm constructing a lambda. So a lambda is a block of processing that's defined locally. It's not a declared function. And this tells the compiler this is a lambda. As long as there's a white space here, as soon as the compiler sees white space and a bracket, it says lambda. Now, so what I'm doing is I'm defining a lambda that you pass it a standard string, and now it says return message plus epilogue. Here's epilogue, okay, that's not defined in the body of the lambda. It's not passed as an argument, okay, it's captured. And I'm going to explain to you what that means in just a second. So it's captured. So now, what's going on here? When the compiler compiles this lambda, it creates a functor. And the functor operator paren, the body of the operator paren, is the body of the lambda. Whatever code is here in the body of the lambda goes into operator paren. And whatever variables I'm using that are defined in the local scope become member data of that functor. Just like when I constructed my functor, I passed it a parameter and became member data. This is just like calling a constructor on that functor and passing it this epilogue. What the compiler compiles is equivalent to that. Okay? So you have to understand that a lambda is just a shorthand way, a quick way of creating a functor. I did it in 1, 2, 3, 4 lines instead of class functor, you know, in the 8 or 10 or 12 or 20 lines that it took me to define the functor. Lambdas are just a shorthand way of defining that functor. So now, what that means is that when I say this lambda captures this epilogue. I'm using, here's a variable name I've used in the body of my lambda that wasn't defined in the body of the lambda and wasn't passed as an argument, but it was declared in the same scope as the lambda above it. That's going to be captured. What happens is the compiler creates a functor, makes this operator paren, and makes that local member data. Makes that member data of the functor. Okay? So, now, what this equals says is that I'm going to make a copy of epilogue here. Now, you want to be careful with whether you make copies or references. Lambdas are designed so that I can construct them one place and I can transport them out of that local scope into some other scope and execute it over here. And if I made epilogue a reference member, if I didn't make a copy, but instead I just made a reference to this epilogue, now I transport it out of that scope. As soon as I leave that scope, the function is done. That variable becomes invalid, and now I've got a reference to invalid data in my functor. So there's two things I can do. I can copy it, or I could create this instance on the heap and give it a reference to that heap thing. And now, when I exit the function, what's on the heap doesn't become invalid. But now I have this nasty little problem that I got to figure out how to delete that from the heap eventually and not forget. You know, I could at the end, you know, if I put it on the heap, that at the end I could call delete. You know, so it's not such a nasty problem, but you got to remember to do that. So now let's go to this code snap. So in the code snap, let's look at lambdas. So what I've done here in this comma, this is just a little demonstration of lambdas. I've told you this is about the syntax for capture. If I say parens equal, I copy anything I use in the body of my lambda that isn't passed to it as an argument, is I do a copy construction of that into member data of the functor that I'm building. If I put nothing, which is legal, it does a copy. By default, it will make copies. But usually we do this just so we can explicitly say, maintain a program, this is a copy. So you can pass it around. Now, I can put a ampersand here that means reference. And so now, this reference is, I'm making a reference to that captured data. My functor is holding a reference to that variable out there. And there's times when you need to do that. If I want to declare, if I have a function, if for example, if I define this lambda in a class, in some member function of a class, and I refer to member data in the class, which I'm allowed to do, the compiler will insist I make this reference. It'll say, you can't make member data, you can't capture member data by value, you have to capture it by reference. Error message says something like that, okay? So the times when you will need it, and that's fine because the class isn't, that instance isn't going to go away when you leave the function, so the reference makes all the sense in the world. Not a problem. I can be more specific. I can say, if my lambda uses two different variables from that local scope, I'm not passing either one of them in as an argument. It's using local var1 and local var2. I can say, if I say local var1, this is a copy, makes a copy. If I say ampersand local var2, it makes a reference. Passes by value, passes by reference. That's the syntax for lambda. Okay, and you can go down and look at the rest of the code snap at your leisure, and let's go back to our example. So, so I just have this little lambda, and what I do, just to show you that you can invoke it, so this lambda is returning a string and accepting a string. So I need the invoker that accepts a callable object, accepts a parameter, and will return something. And I provided it, and the compiler will pick from using type inference, it'll pick the right invoker to invoke. So now I just say, here, I created my lambda. Now I'm executing the lambda directly. I'm just saying lam, hello, CSC 687 world, and blah. Here, I'm going to invoke it. So I'm invoking the lambda, passing it, so I'm passing it this argument, okay? So here's the argument, here's the callable object. Now I've got to tell the compiler doesn't do inferencing on the return value, so I got to tell it this is going to return a string. Okay? And you don't have to worry too much about when do I say that, when do I don't, because if I didn't include it, the compiler, it won't compile, and I get a nice little error message that says, you have to tell, you have to tell me the type you're going to return. It doesn't say exactly that, but the equivalent of that. Okay, and if we run it, it runs. Hopefully. Yes, it did. So here I'm invoking it directly. Here I'm invoking it through the invoker. So what I'm really illustrating is, aside from the little background on lambdas, I'm illustrating that this invoker accepts a lambda. We already saw it accept a functor, and it does all the type resolution necessary. So I've expanded the type of I've overloaded the invokers. In my original simple demo that we did last time, I had just one particular invoker signature. I think it was a void void. Here I have a void void, I have a param returning void, and I have a param returning some return type. And it's by type inferencing on that overload is picking the right one. Okay? Very, very useful. Very, very useful. Now, easy stuff out of the way. Let's look at the complicated stuff. So here's function pointers. Now, function pointers basically are relatively simple if they're global functions, if they point to global functions. When they point to member functions, it gets a lot more complicated. The syntax gets more complicated. Okay, so I start out by pointing to global functions. So here, I'm declaring a alias function pointer void void to point to this is a declaration of a function pointer that takes no arguments and returns void. How do I know it's a declaration of a function pointer? You go to the middle, star, so I'm a pointer to paren a function that returns nothing. So I'm a pointer that points to a function accepting no arguments and returning void. That's what this says. So I have function pointer void void. Now I'm declaring a different type using a parameter, and I can make these usings declarations be templatized. So template type name param, function pointer void param equals function pointer pointing to a function that accepts an argument param of type param and returns nothing. Okay. Finally, I have template type name return type name param using function pointer return param equals return function pointer pointing to a function that accepts param and returns this type return. Whatever I plugged in here, that's the type that it returns. Okay. So now I illustrate that. I have a global function, void say. So this is void void. This is a global function, void void. This is a global function that's param void. And here's a global function that is param return. This particular one, it's just a little demo, silly little demo, and all it does is it says, are these two things the same? And that's determined by whatever I said here and whatever I said here. So if type ID of param.name equals type ID return.name, param and return are the same type. Otherwise, param and return are not the same type. Type ID is the very, very weak form of reflection that C++ supports. It's the only part of reflection that C++ supports. It's not really genuine reflection. That information is stored in something called the virtual function pointer table that we're going to talk about really soon now, okay, as soon as we get to hierarchy. And so it just goes to that table. Each class that holds a virtual function has a virtual function pointer table. It just goes to that table and looks up the type. That table holds the type name. Okay, and that's all. The C++ doesn't do any more reflection than this, or not much more. Very, very, very little. Okay, so that's easy enough. So now let's run that part of it. And so here's demonstrating non-member function pointers. My name is say, so, blah, 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 blah. It's all doing, exactly what I said, running just the way I said it would, and, you can go take a look at the details. Now, when we get to pointers to methods, it gets a whole lot trickier. I have a class, I regret naming this function pointer. In my machine at home, I changed the name to function pointer demo, and I forgot to upload that version of it. Okay, I have a terrible time with versions. I do. But anyway, this class is not implementing function pointers, it's demoing function pointers. So now I'm going to create, just like I did before, aliases that are part of this function. So here I have function pointer void member. So this is so here is the type name, function pointer return param. Okay, that's the type. So this is a pointer to this member that accepts no arguments and returns nothing. So in this case, I didn't need these template arguments because for this particular definition, I'm not going to use them. But I am for the other ones. For the next one, I have function pointer void param member. So now this is here's the type, so this is a pointer to a member of this type that accepts param and returns nothing. Okay? You with team on your shirt. What's your name?
Zexin. Zexin, Z-E-X-I-N.
Okay. Zexin. Zing.
Zexin. Zexin.
So Z-H-A-N-G?
Z-E-X-I-N.
Z-E-X-I-N.
Yeah.
Justin.
Yeah.
Something like that. Okay. I'll do the best I can. So, make sense?
Yeah.
Okay, good. I have to say your name about 7 times before I remember it. Okay, I'm an old guy. My memory is failing, So, I'm demonstrating invokers, an invoker for callable objects that take no argument and return nothing, that take a param and return nothing, that take a param and return something. Okay? These are not function pointers to methods are not callable objects. A callable object is something I can take that object, slap parens on it, and that gets an invocation. Functor, slap parens on it, give it whatever argument it wants, if it wants any, and I get an invocation. Lambda, slap parens on it, whatever argument it wants, if it wants anything, I get an invocation. A function pointer to a global object, function pointer, slap parens on it, I get an invocation. But with pointers to members, I need two things. I need a class instance and the pointer. It's no longer a callable object. It's related to it, and I'll show you one way. There's a couple of ways to do that. But now, so now I'm going to create member functions. So this is the constructor for that class. And so I'm just accepting a param and storing it away. Here's a method that is a void method, void member. Okay. Here is a method that is a void param member. Here is a method that is a return param member. Okay. So I'm illustrating those three signatures for members. Now let's look at the implementation. So for global functions, it's fairly simple. So here's the global. I just created a global function say, and now I'm invoking it. Now I can use the invoker to invoke that global function, and it's using type inference to pick the right invoker, the invoker for callable objects that take no arguments and return nothing. And now I am now I'm invoking that say. Now I'm going to create a function pointer, void pSay equals say. All I'm illustrating is that say really is a function pointer. The name of a function really is a function pointer. So I'm trying to convince you that by creating what is obviously a function pointer, because I declared it that way. I'm just assigning say to it. And now I can execute it, and I can invoke it. Yeah, name of a function really is a function pointer. Okay, now same thing for say type. Now this is a callable object that accepts a parameter, returns nothing. So here I'm just invoking say type, that global function. Now I'm just executing it. Now I'm going to use my invoker, and so here's say type and the argument that I need to pass it. And now I have to tell it so I'm telling it the type, the complete type So what I'm doing here is, so this is, I'm telling it what the type of that function pointer is, and I'm telling it what the argument is, and I'm using it. And now I'm going to do the same thing I did before. Now I'm going to create a function pointer. Instead of just using say type, now I'm going to create a function pointer and set it equal to say type and invoke it and use the execute it and use the invoker. It's really doing exactly what I did with these guys, just to convince you that, yeah, the name really is a function pointer. So now I'm going to call a global function with an argument and return value. So here's bool result same of bool true. So I'm passing in, I've templatized it on the same arguments, and the value of that is true, but it's going to ignore the value. It's just going to look at these types and say, are these types the same? And it'll come back and say yes. Here's result 2. Now I'm using the invoker, and I got to tell the invoker what's the return type. And then, if result 1, blah, 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 blah. Just printing stuff out. Now, call function pointer with argument and return type. Now I'm going to use the same function. So result 1 equal pSame. I'm just executing pSame, the global function pSame, and uh, using the invoker, and now I'm printing out the results. So, a little tinkery, but not too bad. Here's where it gets mind-numbing. Now I'm going to demonstrate member function pointers. So I'm going to call this member function directly. So using TBI, so this is a bool int, TBI, bool int, using TBI equals function pointer bool I. TBI, here I'm creating an instance of that, 42, and now I'm saying fp.say. So here I constructed the fp. Now I'm saying I'm calling fp's say method. Okay. Now I'm going to call the member function say with through a function pointer, TBI colon colon function pointer void void member p VMI. So I've declared this pointer to a member function that accepts, returns nothing and accepts no arguments. And I set it to address of TBI colon colon say. And now I execute it. That's a little weird. So here's the instance FP dotting on to the contents of that function pointer with no arguments. Syntax isn't obvious, but that's the way it works. Okay. Now I'm going to use the invoker, and this is not a callable object because I have an instance and I have the function pointer. What a function pointer to a method is, really, I have this instance, and that function pointer is an offset from the top of the function code for that method. So here's the method, code for all its functions. The function pointer is just an offset from the top of those functions down to the function I want to call. That's all it is. Now, invoke member function pointer. Now those invokers are expecting a callable object. So I need a trick, and the trick is I'm going to use a standard function. And for you guys who took SMA, standard functions are very like delegates. They'll bind to stuff. A delegate will bind to a lambda, and a function pointer will bind to a lambda. But a standard function will bind to a lambda, but it'll also bind to this member. So here I say, standard function void TBI by reference. So I return nothing and I accept a reference to a TBI. This is this member function pointer. Cove, callable object void, okay, equals the address of TBI colon colon say. And now cove is what's happened is function, any standard function is a callable object. And so now I can invoke it with cove in the function pointer. And I do this, now I'm going to do the same variations with a function that takes an argument and with a function that returns a value, and that's all here. And the syntax is not so obvious. Syntax is not so obvious. Now, I don't expect you to pull this down, look at it until I remember all that stuff. I don't remember all that stuff. I write these kind of demos to figure it out once, stir it away, I know where it is, when I need it, I go and I look at how I did it. That's what I do. It took me the better part of an afternoon to get all the syntax correct. It did. Okay. So my goal is to to show you that callable objects, you can accept a wide variety of callable object signatures with overloaded invokers, and I can pass to them functors, lambdas, pointers to global functions, and standard functions that bind to the member pointer. Okay. Again, you know, where we'll use them for a thread pool, I want to pass work items into my thread pool. My thread pool is sitting there with a thread pool, the idea is I have a queue of things I want these threads to do. I spin up 5 or 10 threads, some number of threads, and each thread only has one function. That function, I can't change the function in the thread. I give it one function. Well, what that function does is it goes to the queue, pulls out a work item, which is a callable object, invokes it, comes back to the queue, picks up another callable object, invokes it. But now I can have all kinds of different things that are work items with different signatures because of this. Okay, cool. Yes. Okay. But again, if you're sitting there saying, oh my gosh, how am I ever going to remember that? My answer is don't. You know, it's here. When you need it, you know where it is, you know what to look for. That's the way I treat it. Okay. Any questions before we, yes?
For the invoke member function pointer and this std function void t.
What line are you at?
I haven't done down in the function pointer that cp after the call member function demo.
Well, these are all call member function demos. The first one is void void. The second one is
Up a bit.
up a bit.
Yeah. Let's say up a bit. Let me check. Line 95 and 94.
Line 94. So say type is accepting
No, line 88. I don't know why my version.
line 88.
In the browser is not the same as in the Visual Studio. So in this code, I don't know if the reference TBI colon say is a member function in the
Say is a member function in the class.
Function pointer class, member demo class.
Yes.
But std function is accepting a global function or a callable object, right? So how can it accept a member function?
So what's happening is this is just an offset, okay, and
and then if it's a callable object, so why the function return type in the std function in this sharp bracket is void parentheses TBI read by reference.
well,
It's not passing a reference into
so
it.
what's happening is, yeah, I'm passing, so what's happening is this standard function is a function that accepts this this member pointer. It's a function that accepts this member pointer and returns void.
But this function itself accepts nothing.
No, this is the member. So what's happening is this is the member function that so see the standard function, what it's doing when it's binding this is binding both to the instance and that function pointer. This syntax here's a place, the syntax really doesn't look like what it's doing, I think. Okay. So this is really just the way this is written is an artifact of the way standard function was implemented.
So do you mean that the meaning of why translates TPI by reference is that this code does passing a number function into it and also call a
It's-
class instance.
So this is binding, yeah.
So when the compiler says the TPI by reference, it will recognize it as a class and an instance.
Yeah, remember you told me in your class design for Project 1, you used memfun? Memfun. This is working just like memfun.
Yeah, that's why I said. Okay.
It's working just like memfun. Okay? And actually now the standard says that memfun is deprecated.
No, this is FUN, but FN is still kept in the standard. MEM underline FUN will be deprecated in C++.
I thought okay, I misunderstood. I thought you were using memfun. There is a standard MEN underscore FUN.
Yes, yes.
Okay, and what that's doing is taking a member function and so that you can invoke it like it was a global function. It's that memfun is binding both to the instance and the function pointer, and now I can invoke it as if it was a global function. And that's what this standard is doing. Same thing. This is doing the same thing that memfun does.
Oh, so
And memfun is deprecated because this is what they want you to use. Okay. This standard function does a bunch of other things, but yeah. Okay.
Professor?
Yeah.
I remember there is a bind function in standard library.
Yeah, this is doing things similar to bind. It's doing things. So you could use bind.
Okay.
You know.
I remember
Yeah,
from
absolutely.
instance.
The mental model, I think, for the design of the C++11 was that standard function is your go-to. Probably don't need bind in most cases anymore. You don't need memfun in most cases anymore. Standard function will do them all. Okay. But you're absolutely right. You could do this with bind. Okay. So now I want to do a quick look at simple demos for STL containers, and then we'll start talking a little bit about hash tables. So this is at repository. Probably I have it on my list here. It's in repository CPP. Let's see, STL containers I do. So now I have a demo for each of these, for each of the containers in the standard template library. There is an array class. So there is a native array. This is different than the native array. There's a native array, and if I pass a native array to a function, I am essentially passing a pointer to the array, and I got to pass the size of the array. The only thing this array class gives you is the ability, I just pass an instance of the array class, and now your code inside the function can ask the array class, how big are you? It's still fixed size. It's not a variable. You know, that's vector is the variable array. So this is an array class. There's a deck. Deck is a doubly ended queue. And it wants to support constant time operations on either end. So a vector pushing back is constant time. Because you're at the end, you're just adding one more. But there is no push front. You have to insert. And when you do an insert, that's a linear time operation because you got to go to the last element, move it up, move it up, move it up, move it up, move it up to make space for the insert, and then comes the insert. So operations on the front end of a vector are linear time operations proportional to the number of elements in the vector. while pushbacks, operation on the end, are constant time. DEC is trying to support constant time operations on both ends. It does exactly what the vector does. It gives you expandable, contiguous, supposedly contiguous memory. That's the model. But it's constant time on both ends. And it implements it by having a block of memory for the front end. So you're doing pushbacks here, push fronts here. A block of memory at the end, you're doing pushbacks here, and a block of memory in the middle that binds all three together. It's not contiguous memory, but the indexer makes it look like it's contiguous memory. For years, the Microsoft implementation was buggy, and I didn't use it, okay? But I still don't use it much. It has the nice advantage that it's constant time on either end, but it's actually, for pushbacks, it's going to be slower than vector. Vectors are faster if you're just working on the end. So I typically use vectors. I don't use DECs. If I really need to do operations on both ends, a lot of them, then I would use a DEC. Forward list. So the STL for years has had a doubly linked list. This is a singly linked list. List is the singly linked list. Map is an associative container but it's ordered. So the map holds a binary search tree. It's holding elements in that binary search tree. The tree is balanced using the red-black algorithm rather than the AVL. I don't know why they didn't use AVL, but they used red-black. So its access time is log n, where n is the number of elements in the container. Native array is a genuine native array, but it's here to illustrate that all of the STL operations, iteratings and stuff like that, work on native arrays. Q is a standard FIFO queue. And the queues and the stacks don't give you access to the internal components. You just see the stuff at the ends. For the stack, you see the stuff at one end. For a queue, you see the stuff on either end, but there's no index operation for it. Although if you want to work at it, you can see them. Set is set is also an ordered associative container. The difference between set and map is that map is key value, set is just a value. So for a set, it's just a binary search tree order of the values. For map, key value pair, so we have a binary search tree holding pairs where they're ordered on the key. Instead of being ordered on the value like the set, they're ordered on the key. Okay? Stack is a LIFO, last in, first out container. This unavailable thing was just a demo that I was, showing them all, and I'm going to remove it. A string is an could we not have a conversation, please? String is an STL container, believe it or not. All of the things that the containers provide, begin, end, iterator, string has. Okay, string is a STL container. Unordered map is a hash table hashed container. So, and we're going to talk more about them in a few minutes. So it is a associative container, unordered pairs, associative container of unordered pairs. And I'm going to talk in a little bit of detail about that in a minute, a few minutes. Unordered set is just like unordered map. It's a hash-based container, but the set is just a container of values, and so it's hashed on the value, and just the value is stored. A unordered map is a pair which is hashed on the key, but the key and value are stored in each element. And vector is a contiguous memory that's a constant time on the end, but linear on the beginning. If I insert in the beginning, I get linear time operation, because I got to move all those elements up to make space. Let's just look at one or two of these. Let's look at list, just to see the kind of things that are here. So here's list. So I start out with saying implements doubly linked list with each element stored independently in the native heap. Operations on either end are constant time, while operations in the middle are linear time. Okay? As long as I have reference to each end, I can do linear operation. I can do order n operations. And now I just use it. So here I have a list. This is the modern, as of C++ 11, initialization for all the STL containers can be initialized this way with a parameterized list. Now, you'll see this as, this is a list of lint equals paren stuff. Either way is acceptable, but there are a couple of places where if you use the equal, there's some ambiguity. So we tend to favor not using the equals here, because this is never ambiguous. So, you know, it's not a big deal. If you use the equals and it's ambiguous, then you just go and remove the equal. Okay.
What exactly is the ambiguity?
I don't remember the case. I don't have the case in my head this instant where the ambiguity is, but it is that there are a few cases where there is an ambiguity about it. You know, if you're interested, send me an email and I'll dig it out and look at it. You know. Scott Myers in his book Effective Modern C++ talks about that. It's a really nice text. And now I'm just, you know, I'm doing stuff with it. Just simple little things. So operations on both ends are efficient. Push front, push back. Okay. So vector doesn't have a push front. List does. Vector doesn't have a push front because it's a linear time operation, and they're discouraging you from using it. You can put something in the front by inserting. Okay. But list provides both push front and push back, and I'm doing it, you know, and I can pop from the front and the back. Insertion is linear time, so I insert, you know, some value. That's a linear time operation. And list can be walked back to front as well as front to back. So here I'm using a reverse iterator, and you know, so while reverse iterator not equal to lint.rn, you know, so this is written just like forward iteration. I could do the same thing with the forward iterator by starting at the back and decrementing, okay? But a reverse iterator just lets you use it using exactly the same syntax as the forward iterator. So all of these work like that. They're all examples like that. You know, here's the unordered map example. So, you know, holds hash table of key value pairs in the native heap. See ordered set nodes for discussion of hash tables. Like all the other STL containers, this implements copy construction, move construction, copy assignment, move assignment, and destruction. Traits are key type, value type, iterator, and I'm going to talk about that in a couple of minutes. So don't worry about traits. So all of the, you know, I'm just giving really simple exercising of each of the container types. So I don't always remember the syntax. You know, if there's some container that I haven't used recently, I'll have forgotten what the syntax is. I go here and look it up. Oh yeah, okay, away we go. So, or you can go to cppreference.com. You know, same deal. But what I think might be valuable for you is I certainly wouldn't try to commit all this stuff to memory. You don't need that. But I might print it out and just skim over it, you know, getting the idea of how each of the containers works. Okay, with that, let's talk about hash containers. So, before the STL had hash containers, they didn't have hash containers until C++ 11. I designed a hash table container, and we used it for class projects for a while. There's one issue with this, which I'll talk about in a minute. It's correct, works, but there's one thing I didn't do in the design that I'll talk about in a minute. Let's see how hash containers work. So, the reason hash container is, we say it's based on a hash table, is that there is a table of addresses. And when I want to store a key value pair in that, I use a hash function on the key to calculate an address. Okay, and what I do is I go, you know, if this was empty, I hash to that address, then I create a node that has both the key and the value here, okay, and I make this address slot point to that node. Okay, it's just a table of pointers. And these are all null. This is very carefully initialized to null, has to be, before you start, because when you walk down, you need to know, is something here or not? If the pointer is null, there's nothing there. If it's not null, there's something there, and you're going to go try to dereference it. And if it was just garbage, bang, up goes an exception. So you have to initialize it with all null. Now, there's no guarantee that a hash function will hash two unique keys. They may hash two unique keys in the same address. Typically, they'll be different, but nothing guarantees that they won't hash to the same address. That's called a collision, hash collision. You know, imagine this table holds 1,000 items. I can store 2,000 items in it. But if I have the same table size, I don't change the table size, that guarantees that I'm going to have a bunch of hash collisions. Now, hash algorithms are really interesting because what you want is a hash algorithm that does a uniform distribution of computed addresses for a given key. Given key, you want it equally probable that that computed address will be anywhere on the table. It's easy to design a bad hash function which biases it toward lots of addresses computed down at this end of the table and very few computed up at this end of the table. And you say, so what? The so what is that now if I have lots of addresses at the bottom end of the table, it's much more likely that I'll have long chains going up in that bucket. Now my time, we say that a hash table is constant time. It's constant time to compute that address, but now I got to walk up that chain. So if I start to have long chains, my performance goes from constant, it starts to go up asymptotically as linear performance. So what good hash tables do is, as soon as the table has some load factor above some threshold, and it'll mean still quite sparsely populated, okay, it will go away, double the size of memory, copy those, you know, these pointers into that expanded table, so the table is always relatively sparse, so it's almost always constant time performance because the node chains are short. Understand that when you go off and reallocate more memory, you can't just pick this whole chain up because the hash algorithms are now different because the table size is bigger. So you got to rehash every one of those elements in the container. Okay, but you know, that's not going to happen very often, and so most of the time your performance is constant time. So you'll see in my notes I'll refer to it as almost constant time. That's because of that. If an interviewer asks you the question, you say almost constant time. And they'll say, explain that to me. What do you mean by almost constant time? And then you'll say, okay, I may have some buckets that have, you know, a bunch of collisions, and so now it's no longer not only the time to compute the hash, but now the time to walk up that bucket list. You know the term something being on your bucket list? Well, something's on our bucket list. Okay. They mean something different. You know, there was a movie about the bucket list. Bucket list means before I kick the bucket, here's a list of things I want to do. Kick the bucket meaning I die. Okay. So before I die, here's a list of things. So, but anyway. Now, the reason we have iterators and containers is that this iteration process, both as I iterate, when I iterate, I want to go to this element, 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 as I iterate, as I plus, plus, plus. So what's got to happen is, you know, if I'm sitting here, if I'm not at the end, I got to go up here. If I'm at the end, I go down to here. And if there is something here, I go up. If there isn't, I move to the next one. Okay. So that iterator has to know about the structure of this container. And so each container has its own iterator. The iterators are smart pointers. Each container has its own iterator, and that iterator understands the structure. So for a vector, I'll say, to get a vector, an iterator, I'll say standard vector of string, colon, colon, iterator, and I get an iterator that knows how vectors are structured. If I say, if I want an iterator into my hash map, into my unordered map, I'll say unordered map of string, string, colon, colon, iterator, and that iterator knows how to walk through this structure. Okay? How are we doing? Some of you are responding, say, yeah, I got it, I got it, I got it. And some are saying, what is this crazy guy talking about? If you're in the latter category, this is typical question for interviews. Typical questions for interviews. So, if this doesn't make sense to you, look at it. Come back and ask questions of me in the open office hour. Ask questions to the TAs, because very typical. You go for a Google interview, and they start asking, and you can't, and you don't give them a good answer, you're gone. You're done. Or Facebook, or PayPal, or Visa. Okay. Okay, now, and so, you know, my iterators, my iterator acts like a pointer, just doing, you know, going through contiguous memory, but it's not. It's doing these complicated things. It's a smart pointer. Using the interface that I show there at the top. Plus, plus, contents of, selection of, pre-increment, post-increment, pre-decrement, post-decrement, and so on. Okay, now I want to talk about hash containers. So this is a design, my design of the hash container, the hash table. It is of absolutely no importance for you to understand the design of my hash container. But I am illustrating the way templates work, illustrating template policies, illustrating template traits, and those are very important things for you to know about. That's why we're going over this container. So here, containers often must grant friendship to their iterators, so I'm granting friendship to my hash iterator because this hash iterator has to get into my internal data store and walk through it. It has to understand it and get access to it. I have key, template type value, template type hash. There's lots and lots of hash algorithms for any given type. There's a bunch of them. There's a famous computer scientist. His name is Donald Knuth. He's written a series of volumes, big, thick, fat volumes, okay? And if you're a computer science student, how many of you are computer science students? Yeah. Know about Donald Knuth.
Yeah.
Look at some of his, yeah. So he has a series of, I think it's now 5 volumes.
The art of computer science, the art.
Yeah, the art of computing, or art of something like that. But anyway, a series of, I think he was faculty at Stanford. I'm pretty sure he was faculty at Stanford. And he invented a lot of the algorithms. He was one of the prime guys in inventing good hash algorithms and one of the first guys to help us understand what it took to write a good hash algorithm. I don't know how to write a good hash algorithm. Okay? That's one of those things, you're never going to know everything. It's one of those things I set aside. Okay? I read a little bit of what he has to say, you know, and at the time, but it's not standard working knowledge for me. If you're computer science, it might ought to be standard working knowledge for you, okay? But anyway, so this is a template policy. The first two, key and value, are fundamental to this container. Every hash container has to have a key, and every, if it's a map type, then it's got to have both key and value. But the hash is a modification of its behavior. Has to have a hash. But the hash function is just modifies the way that guy does his simply by giving it, here's how I calculate that address. That's all it does. I calculate it this way. Oh, I want this other policy because I know I'm going to be doing this, blah, 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 blah. And so maybe I would favor, if I know my hash table is never going to be heavily loaded, I might favor an algorithm that didn't do such a good job of uniform distribution, but was fast. I might favor that for applications where the hash table didn't hold a lot. But if I have a hash table that's going to hold a huge amount of stuff, I absolutely would want the most uniform hash that I could get, even if it was a lot slower. So this is a template policy. Now, what are these things? I call them traits. This, and this are traits. The STL calls them traits. What are traits? So notice that, suppose I want to write a template function, and I want it that wants to find the sum of the values in an unordered map. And I want it to work for maps that are string-string. I want it to work for maps that are string double. I want it to work for maps that are string int. Do I have to write those three functions? No, I don't. But how am I going to declare that sum? Here's a template function. I don't know what it is. I don't know what is this is the value an int or is it a double? What do I declare? So here a very smart thing was done. Type def key type. This is a universal name for whatever that type is. This is a universal name for that type. So if that type is an int, key type. If that type is a double, key type. So now I just declare key type sum, and I'm done. It'll work whether the key is a string or an int or whatever, because the type def is resolved at application time when it's really compiled. Okay, when the compiler knows the type, even though I didn't know the type when I wrote this function. That's what traits are all about. I promise you, Wei Heng, I'm going to ask questions about policies and traits on the midterm. I've said that so many times, I couldn't possibly put all this up, but that one I will. Okay? So. And anytime I see your eyes kind of glazing over, you say, oh, then I point at you and I say, embarrassment is a wonderful tool. Embarrassment is a great tool for a teacher to use. Okay? It's a little prod that says, okay, pay attention here. Wait, Hank. It's a curse for me to know your name in this class. It is, because I'll pick on you. I only pick on Wei Heng because he's smart and he knows what he's doing, you know, but I saw him kind of wavering there. I thought he wasn't paying attention. But anyway, so traits. Iterator. I want to say iterator. Okay, in my function where I use sum, where I'm calculating sum, I have to iterate. No, there I'm not calculating, I'm not hashing, I'm iterating, literally iterating over the entire collection. I have to visit every single element, so it would be slower to hash than it would be to iterate. So I'm iterating over it, but I don't know the type, so this allows me just to say iterator. So that works. Okay, great. And I have a constructor that defines the initial value of the table. Now, I said at the beginning, my implementation, I think I said, has a limitation. And the limitation is I'm not resizing the table. That's something I meant to do when I did the design. My class needed it for a project. I didn't have time to do it. I gave it to them for the project because it was small stuff. It wasn't, you know, they weren't going to save a lot of stuff. And I always meant to go back and make it reallocate memory when the load factor started to get unacceptably big. But along came the standard, unordered map. I'm not going to do it. I'm never going to do it. Why do it? Because the standard unordered map is fine. That's what I need. So. We're getting close to being done here, so I might go a minute or two over. I've ended a minute or two early, so I may go a minute or two over today, so just bear with me. So destructor. So now I got to go across the table, up the, and that can get messy. So I factor this into two functions that are now each simple. There is a delete node chain. So if I'm sitting at the root of a node chain, I call this, okay? And now what this does is a recursive, delete node chain. I call myself. But notice I don't delete before I move to the next one. I delete when I come back. Because what I want to do is, what I'm doing is the recursion is essentially a push on the stack. Push, 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 pop, 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 pop. If I deleted on the way up, delete, and then pick that guy and go next. It's deleted. I can't go next. Okay, I gotta walk up the stack. Now, delete the last one. Delete the last one, and now I'm just popping back because those addresses are stored on the stack. So I just pop, 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 delete. So it's really simple. And now my destructor is really easy. For I equal, I just step over the table, delete node chain. Because I initialize the table to have 0 values, if there isn't a bucket there, if there's no node chain attached to it, if p node equals 0, return. So simple. Just that little factoring took that messy little, is it overwhelmingly difficult? No, but this is a whole lot cleaner. Easier to maintain, easier to understand, easier to test. Single responsibility principle. So there's more here. Inserting nodes in a hash table. Does this container hold this key? Find node, blah, 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 blah. I don't think there's any point in you going over and looking at that. I think you want to understand these first slides we talked about. What are policies? What are traits? You know, what's the syntax for templates in this real situation, not these little toy cases, but here's a real situation where I'm trying to do something useful. What's the syntax? So it's good for that. Okay. Give me another 30 seconds and then we'll break. So